Hello, my name is Lady Leonor da Costa, and I am teaching Ancient Mathematics 1 for us today. This is part 1 of 2. This is class 1 of 2. This part just gives an overview of their mathematical systems of the Babylonian/Sumerian civilization and the ancient Egyptian mathematical systems. So part 2 will be practical computation. So if you're wondering how to do the arithmetic with numbers like these, that's the course that you want to take for that. I've required this one as a prerequisite for the second one, and you will not have to do anything super complicated. I mean, if you can like take square roots, we're gonna do quadratic equations and fractions. So if you can handle those, then you can handle what you're about to do. Oh, we love the quadratic equations. All right. So our objectives today, we're going to look at the numeration systems of ancient Babylon and ancient Egypt, and we're going to see how they compare with both each other and our modern system. So I'm coming into this. I know that a lot of my regular students are math nerds. These are people who are interested in differential equations and things like that. However, I cannot assume that all of my students are that way. And so I'm going to start by explaining some basic things about numeration systems. Please stand by if this is boring to you. So our system is a base 10 system. The base of a numeration system is that number where it bumps over into the next column. So we go up 0 through 9, but then the next number is 1, 0, right? It's 10. So, and then we go up to 19, and then we click that 10's column up 1. So our base is 10. Every column is going to represent a power of the base, and numeration systems that have a larger number for a base, like for example, the Mayan system with base 20, they have a sub base that's some kind of divisor of the base. So in the case of ours, we occasionally use 5. So think about like how when you do tally marks, if you have you do 5 tally marks and then you do another 5 tally marks. So that's you using 5 as a sub base. And our system's base is 10. A system with a base of 10 is called decimal. So our system is a positional system, meaning that digits mean something different if they're in different positions. So for example, the digit 4 can mean 4 if it's in the ones column, 40 if it's in the tens column, 400 if it's in the hundreds column. But that's not universally true for all number systems, just ours. In fact, the Egyptian system that we're going to see today is non-positional. Numerals are the symbols that we write for numbers or recognize as meaning numbers. And we use 10 digits as our numerals. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are our numerals. Okay, so we're going to see what numerals look like in other cultures as well. We also have a kind of an interesting distinction between ordinal numbers and cardinal numbers. So ordinals are like first, second, or third. They express the order in which something is. A cardinal number is how you count things: 1, 2, 3, 4, 5, 6. In some other languages and cultures, there are different types of ordinal numbers or cardinal numbers. So like in Japanese, they have different cardinal numbers for different, like, I know I says ordinal, I need to fix that, it's cardinal. They have different cardinal numbers for different kinds of things. So like things that are flat like pieces of paper have different numbers than things that are long and skinny like sticks. Also, we use fractions in our system. Those are not universal to all systems, although the two we'll be seeing today do use fractions. So I have to explain this distinction to my mundane students a lot, but decimals are a different form of a fraction than the simple fractions. So 3/4 is a different thing from 0.75. 0.75 is the decimal fraction representation of 3/4. For 3/4, it's not that big of a deal, but it's when you start getting repeating decimals that it becomes an issue, because 0.3 is not the same as 1/3. 0.3 is 3/10. So it makes it a little difficult if you conflate those two because they have different values. But just realize that we have these different ways to represent fractions. Also, 0 is an interesting number because not all numeration systems have the number 0. I know it seems weird to us that there would be a numeration system that could actually do mathematics that does not have a 0, but we are going to see 2 of them today. There's 2 roles that 0 serves, and one of those is to be a placeholder. So in the number 400, those zeros, those are placeholders. They're telling you that the 4 is in the hundreds column and not in the tens column or the ones column or the thousands column. Okay. There are also a computational 0. That's a distinct function that 0 performs. So for example, if it makes sense to do 0 times 4, that is going to be a computational 0. Yeah, okay. All right, so let's take a look now at the Babylonian system, and then we're going to take questions, and then we'll go on to the Egyptian system and take more questions. Here's a little bit of a timeline, and just a quick disclaimer, I am not a historian. I am a math teacher mundanely, so please pardon me if my little timeline's a little off, but the basic idea is that we have evidence that measurement had been invented by 4000 BC in Sumer, in ancient Sumer. We found these like little tags with numbers, with measurements on them. So we know that somebody was measuring stuff back then. As far as like a fully formed mathematical system, we start to see that around 2600 BCE. And then the Babylonian Empire takes over from Akkad, and then we really start to see some stuff happening. So we see fractions and algebra and quadratic and cubic equations during the Babylonian Empire period in that area. So there were 3 empires that were in the area at the time: the Sumerians first, then the Akkadians, and then the Babylonians. So their numeration system was written with wedges. So this is cuneiform script, and I'm going to be the first to admit I cannot read cuneiform, and I can't write it either. But if you would like to try it, if you make like a little, I don't know if you've seen these little, that's almost like a booklet made out of wood or something, and then they have wax smeared on it in like a little indentation, and then you can mark on it with your stylus. So the stylus makes wedge-shaped marks in the clay or in the wax, and you can make several types of marks depending on how it hits. So like if you hit it directly on one edge, you get like a long wedge-shaped mark. If you hit it just on the corner, you get a different kind of mark. But you can kind of see that in the background image on this slide. That's Plimpton 322. That's a clay tablet with a table of Pythagorean triples on it. So Babylonian mathematics is heavily reliant on tables. They found lots and lots of cuneiform tablets that have some mathematical content on it. Some of it's more accounting, some of it's more like theoretical problem solving, but the basic idea is that here's a few of the tablets that they've found. Some gives you an example of some of the content. Plimpton 322 is a table of Pythagorean triples. YBC 7289 is a famous diagram showing the square root of 2. We'll see that one in a bit. And this one in the corner, this is the earliest known multiplication table. And it's showing multiplications that were used in various practical calculations. So the Babylonian numeration system has a base of 60, and it uses a sub base of 10 because 60 is pretty big. If you wanted to make like 60 little wedges, nobody's going to be able to count that. The human brain can process 3, maybe 4 things to take them in at once and kind of count them in your head without actually going 1, 2, 3, 4. So the max you can do that with is about 3 or 4. So you really don't want to be going all the way to 60 with that. So they use a sub base of 10. So every time they hit 10, they cue the sub base up. And then once they reach 60, then they go over to the next column, so to speak. Okay. Let's take a look at some of the numerals. So you can see that the you're going to start off with 1, 2, 3 being, collections of 1, 2, and 3 wedges, vertical wedges. But then you start with 4. Notice that at 3, they break off and make the next row of wedges. And this is because of what I had said before about how your brain can count up to 3 with 3 or 4 without like counting 1, 2, 3, 4. So this is able to be read more easily, to have not like 5 in a row, but like 3 and then 2 would be a better configuration. And then you can see that when we get to 9, we're looking at a 3 by 3 array. But then when we get to 10, we now look at a sideways pointing wedge. So this is a wedge that's made with just the corner of the stylus. And then you can see that it's an additive system. An additive system means that if you see a 10 and then a 1, it means 10 plus 1. So then it just keeps going like that until you get to 5 10s and 9 1s. That's 59. So then what happens when you move over to 60 in the Babylonian system is that you start with 1 again. But the Babylonians do not have a placeholder 0. They don't have a computational 0 either. They don't have any 0. At least they didn't originally. So you just had to kind of infer from the context what that number was. So if you saw 1 vertical wedge, that could be 1, or it could be 60, or it could be 3,600. It's not clear what it is. So you have to kind of look at the context. So if the context is like how many sheep your neighbor sold you, your neighbor probably did not sell you 3,600 sheep unless your neighbor's very rich. Okay. However, if it's tribute that was being paid to the king, it's definitely not going to be 60 or 1. Okay. It's going to be 3,600. So you see how it is. You had to kind of infer from the context. This became quite confusing quite fast, though, as the civilization grew. And so they later developed a placeholder 0. Remember that we're talking about thousands of years of time, like a 3,000-year chunk of time here. So there's going to be some development in there. It's not going to stay exactly the same for 3,000 straight years. Okay. So we still have some remnants of this system in today's mathematics. One of the most prominent ones is that we have 360 degrees in a circle. Now, those of us who took trig or teach trig know that there are 2 other systems for measuring angles. We have radians, which we use a lot in calculus, and then we have grads. Now, nobody that I know of uses grads. I've never met somebody that uses. If you know anybody who uses grads, please let me know because my students ask. But grads was set up to be kind of almost a decimal measure of, or almost like a metric measure of angle measure. There's 400 degrees in a circle. So 100 in every, what we would call now a 90-degree angle, a right angle, okay? But yet this system still persists 360 degrees in a circle long after the original system, in which 360 was a nice round number, has disappeared completely. It was also a really good system for astronomy because there's almost 360 days in a solar year. And they were able to record and predict astronomical events with this numeration system. Sexagesimal fractions, they were also very accurate. We'll talk some more about those in class number 2. But this was a system, this and the Egyptian system were pretty widespread outside of their respective cultures. We have a cat trying to break into our class. So table-based mathematics has a little problem with it. It's kind of kludgy. If you had to look up on a table every time you wanted to do something, your math would bog down pretty quickly. This is why we have kids memorize the multiplication tables. It's not because we hate kids or think they ought to memorize stuff. It's because we need them to have that and not have to look it up so that they can do further calculations like long division or square, find perfect squares or things like that. Okay, so we've got a lot of different things that they can do with that multiplication. I remember one time I had a student who failed my algebra class for no better reason than that she didn't know her times tables fast enough. Because when you factor a polynomial, you have to find, like, say, factors of 24 that add up to 10, okay? And you have to be able to find pretty quickly that they're 6 and 4. 6 times 4 is 24, 6 plus 4 is 10. But it took her like 30 seconds to find each pair. And when I gave her the exam, she did 3 problems perfectly, absolutely exquisite work. But there were 10 on the exam, so she failed. So yeah, this is why we memorize the multiplication tables. But if you don't memorize your tables, or the more common things that you do, then you've got to take time to look things up. And if you had to look things up every single time you had to know what 2 numbers multiplied was, this would be quite difficult. Okay. We're going to see one of the formulas that they had to ease multiplication later in class 2. We're also going to see how they did their division as multiplication by a fraction in class 2. As far as finding square roots, we are not going to do that in class 2, mostly because the hand algorithm for finding square roots is not a commonly known thing in the Western world today. So this would be something that's completely alien to my students. And also we only have an hour. But we will be solving quadratic equations, and they could also solve systems of 2 linear equations. As far as their geometry goes, it's all practical. So they were able to solve a triangle, but they didn't have any concept of angle measure or trig functions, but they had formulas that worked to find approximations. They did know some Pythagorean triples. In fact, they have tables of those, but we don't know how they got the triples. We're not sure if they know that or knew that about what we today call the Pythagorean theorem. Do not get me started talking about the Pythagorean theorem. I will talk forever. My students can tell you this. It's the Pythagorean theorem way predates Pythagoras, and he did not claim to have invented it. So that's a whole other thing. So we don't know if they knew how to generate them like abstractly, or if they were just finding practical, hey, I found a triangle that when I look at the sides, it makes a right triangle. We don't know how they generated that. This is YBC 7289 showing an approximation of square root of 2. And if you look at the digits here, these are sexagesimal decimals. Well, what we would call decimals, this is sexagesimals, okay? It's 1.245110. Any questions about Babylonian mathematics?
There was one question in the chat that I think you already answered, whether they used tables or whether or not they had to memorize things. I think you already addressed that one. And
Yeah,
we have a survey.
Oh, go ahead.
We have a surveyor in the room that uses grads.
Nice. All right. I will let my students know that there is one person on the face of the earth who uses who uses grads. No, just kidding. It's probably more than one. Yeah, they had formulas that they would use, and they probably had the formulas memorized just from use, from extensive use, but the things that went into the formulas they had tables for, and we know they had tables for them because we have found their tables. So any other questions? All right, let's move on to Egyptian mathematics. So here's a little timeline. So Egypt had a bunch of different, ancient Egypt had a bunch of different dynasties and kingdoms and things like that. The Old Kingdom is where the pyramids were built. And we found the earliest evidence of numeration in ancient Egypt using the system I'm about to show you around 3200 BC. So this is very early, before the pyramids. And we don't have records of the exact math that they used to build the pyramids, but we know they had to have had math to build the pyramids because nobody kind of eyeballs a pyramid that big. We found around 2500 BC, there's some guidelines for the slope of pyramid sides. We know that the ancient Egyptians had the concept of slope. It's the reciprocal of our concept of slope, because we use slope as rise over run. They did slope as run over rise. The mathematical papyri that we're going to be focusing on today date to the Middle Kingdom rather than the Old Kingdom. So we don't know if this knowledge was had before, because papyrus deteriorates. It's preserved a little longer in the climate of Egypt, but it still deteriorates. So these are the earliest mathematical papyri we've found, date to the Middle Kingdom. The Rind mathematical papyrus, which is the background for these slides, dates to about 1650 BC. So, and it actually says in the papyrus that it is a copy of an old book. So, so that is not new. This is not like cutting edge mathematical research at that time. This was old stuff. There's all kinds of periods of kings and political unrest and things like that. It's not the topic of this class, but the math we're going to look at was in use in some form between 4000 and 1500 BC. And remember also that things change during a period of time that long. So the symbols that we see tend to turn into like cursive, basically, like people start writing them quick, and the letter forms change, or the numeral forms change. So you won't see exactly those particular numerals in every ancient Egyptian mathematical papyrus. And like I said, I can't read these ancient languages either. So I just know a little about the evolution of the numerals. So here's what they could do. They could do some arithmetic, the same arithmetic we do. They could do fractions. They did them a little different, as we're going to see in the second class. They could solve linear and quadratic equations, and they were of particular concern to them was calculating areas and volumes. And they actually have some formulas for things that we don't have formulas for. An example of one of those would be, there's a formula for what amounts to a fourth of a frustum of a pyramid. So if you take a pyramid, right, and you chop off its top, so now you've got like a little trapezoid cross section thing, and then you chop that in fourths, then you have a fourth of it. And yeah, you can find the volume of that, which from there you can extrapolate to what was the predecessor of a pyramid, which was these, they were sloped on the side, but then they were flat on the top. So here are some of the papyri that you might want to take a look at if you're interested in pursuing this further. A lot of these are problem sets, and these are basically math textbooks. I mean, if you think of like what a math textbook is for us, it's basically used as a problem set, right? To teach people or to serve as example problems. So a lot of these were basically textbooks or example problems. We don't know if they were used specifically for instruction, but we do know that they exist and that they have a wide variety of problems in them. So they may have been reference books for people who were doing math. If they forgot how to solve a kind of problem, it would walk them through an example and then they could solve their own problem. But the Moscow Mathematical Papyrus is one of these. The Rind Mathematical Papyrus is also one of these, and so is the Lahun Mathematical Papyrus. The Berlin Papyrus contains the earliest known solutions to quadratic equations, even before the ones that developed in Babylon. So this is the ancient numeration system. This is the one that was attested back in like 3200 BC. And of course, these are kind of complicated numeral forms. So people started writing them a little more sloppily, a little more easily until things evolved. Okay. But the basic idea is that they have a different symbol for each power of 10. And the system is additive. So if you have like 4 of the 100 symbols, and then you have 3 of the 1 symbols, or 3 of the 10 symbols, and then 1 of the 1 symbols. So you would have, it'd basically be 400 plus 3 plus 1. If you want an example of a system that isn't additive, think of like Roman numerals. Do you remember Roman numerals, how they say IV, and that means 4? That's a subtractive type numeral system. So where you subtract them in certain contexts. These numerals are this is a pretty much universal symbol for 1, guys. Is any kind of little vertical line or horizontal line is going to be a universal symbol for 1. The little I can't remember what the horseshoe thing stands for, but the 100 symbol is a coil of rope. The 1000 symbol is a lily pad. You can see it with its root there. Looks like a Pac-Man on top of a line, but that's a lily pad with its root, with its stem. 10,000 is a finger. 100,000 is a tadpole, and 1,000,000 is a guy going, whoa, that's a big number. Okay. So as far as geometry goes, they had that concept of slope. They also knew some things that we know about geometry today, like things that like vertical angles should be congruent. They could also construct right angles, typically using like a chord with 13 knots in it to make 12 equal sized segments. And they would arrange them into a 3, 4, 5 triangle, and that would give them a right angle for surveying purposes. They did not have the theoretical geometry that we associate with the ancient Greeks. So proving theorems, knowing completely useless facts about geometry, things like that's a Greek thing. Okay, that's not an Egyptian thing, not a Babylonian thing. In fact, ancient math before the Greeks is generally not concerned at all with theory. It's concerned all with practice. Questions?
There weren't any in the chat, but this is a lot of cool stuff.
Yeah, please unmute and ask questions. Ask questions, make comments, share recipes, whatever you got.
So I always have a question
Yes.
if someone else wants to go, but so obviously this is a great start of like understanding these particular things. Where are you taking this, and where, I mean, obviously there's the second class,
Yes.
but like what other branches or things can we explore for those crazy people like me who love math? You know, this is obviously just, this seems like it's the tip of the iceberg and
It
not
is.
like the full iceberg.
Okay. The full iceberg would be more than one course, but it would be way more than 2 courses. But there's a lot of other stuff out there to explore. We can explore like the geometric aspect of it, like what exactly in their geometry were they concerned with. So for example, we see a lot of formulas for shapes that we just generally don't use in Western mathematics. So like Western mathematics is all about these ideal, quote unquote, platonic shapes, right? We look at, you know, volumes of boxes, but we don't necessarily look at volumes of like parallelepipeds or pyramids or things like that. We look at cones, but not pyramids. We look at, you know, spheres, but we don't look at like heaps of things. You know what I'm saying? Like we have a bunch of different, we have a different outlook on what we need math for than they did. So we focus on different things. Another direction that we could take this is to go to a more global perspective and look at things like, compare it with like Mayan mathematics. Another one that I'm considering doing for future is practical abacus. So look at like a comparative look at abacus across the world. I have a number of different abacuses, some of which I've had to build in order to have one, because you can't buy ancient abacuses anymore. I know, it's so weird.
Would you mind going back to the Egyptian screen and saying again what those characters represented?
This one?
Yes.
Yeah. So the one, this is a universal symbol for one everywhere you go. Sometimes it's on its side, sometimes it's vertical, but it's always one. One single line is always representing one, pretty much worldwide. The 10, I'm trying to remember what the 10 was. I don't think it wasn't a horseshoe. It was like a
hobble.
Yeah, hobble. Okay, thank you. The 100 is a coil of rope. And then the 1000, that's a lily pad. And we tend to think of lily pads as just the part on the top, but a lily pad actually has like a root that goes all the way down. And so that's what that is. And then 10,000 is a finger. You can see the little fingernail. 100,000 is a tadpole, because there's probably 100,000 of those in any lake. And 1 million is a guy going, whoa, that's pretty huge.
Is there any knowledge of about how many people who are literate might actually be able to do this kind of math in these cultures?
That is a really good question. This would have been something that your average person did not know how to do. In our Western culture, we educate everyone, we teach everyone these basic sums. And there would be, merchants and people would be able to do whatever arithmetic they needed to for their business, figuring out, like, they'd have a sense of which numbers are bigger and which they could add things up so that they could keep accounts. But as far as like solving quadratic equations, your average business owner does not need to know how to solve quadratic equations. So this would have been an elite skill. And this would have been done by scribes.
think even most scribes would know how to do that, or would it be more a specialized thing?
It would require specialized training in order to do, because you'd have to be trained what those tables were for. They're not obvious what they're for. So you'd look at it and you'd see that there's numbers and you could maybe say, oh, that's math. But think of like how your average layperson might look at a calculus book and go, yeah, that's math, but I don't know how to do that.
Yeah, speaking of which, could you show that Babylonian table again? And I was curious,
Sure.
I wasn't entirely sure how that worked, how you use that.
The table? This one, or do you want to see the
No, the play one.
this one?
Yeah, that one.
Yeah,
What are
I'm
you
not
looking
sure
at?
how it works either, because like I said, I can't read cuneiform. So I tried looking at it and going, okay, because I know the first column and the second column are the multiplicands and the third column is the products. But I'm not sure exactly, because that's like the cuneiform evolves, like it's not always the same, you know, from in that entire like thousands of year period. And so the dot is like sticking the wedge straight in, and then this is like using the edge of the, like if this was your stylus, this is the dot, and then this is the wedge, and then they did a wedge and put a dot in it. So I'm not sure exactly what that means precisely.
But so you think you're multiplying this one by this one to get over to here?
Yeah, I know that's what the description of the image said, but
okay.
But I'm not sure exactly which numbers they represent, because again, there's also an ambiguity that could be like 60 times 11 or something. I don't know.
This leads to one of the two questions still from the chat.
Uh-huh.
One of them is, what do you recommend for trying to write in cuneiform?
I actually have a link for that. Give me just a second. I'm wondering if I can minimize this real quick.
The second question while you're looking was, what about negative numbers? When did those come into play, or with any of this?
Not during these periods. Negative numbers come into play later. Let me see real quick. I'm going to try and get a link up for you guys. Okay, here we go. Because I have a link for how to make those. I knew somebody would ask how to make those cuneiform wedges. Okay. There's the link for cuneiform wedges.
Sorry, I was just wondering if nobody else has a question. In the Egyptian formulas, what did they use for pi?
They used a fraction approximation for pi. I can't remember off the top of my head what it is, because the one it's kind of like when I'm kind of old, I'm 49. Anybody older than me probably remembers using 22/7 as an approximation for pi. It's kind of like that, but it's like a 3-digit number over a 2-digit number.
How accurate was it?
The Babylonians, their fractions and stuff were accurate to like 4 decimal places. But remember, they were only doing like surveying math or engineering math, and they did not have, you know, tolerances and things like that to deal with. They just wanted to, you know, stack up rocks and stuff to make big buildings. So they only needed approximations, and they did not need particularly wonderfully good approximations.
So it seems like 4 digits, they had to do some mathematical work. You can't just measure something and get that, I wouldn't think. So
Yeah,
it be something mathematical to derive it.
Where's the one with square root of 2 tablet? Where did that go? When you have base 60 fractions, you can get to what would be 4 decimal place accuracy pretty quickly. Just because the fractions get real small real fast. So this right here says 1, 24, 51, 10. So that's 1 plus 24 60ths plus 51 36 hundredths plus 10 whatever 60 cubed 1 over 60 cubed is 200.
But I wouldn't think they could just measure this thing on this tablet and get that. You'd have to derive it somehow, right?
No, the tablet is just recording what value they got.
So do we have an idea how they got the value?
We don't know. We know that they had it. We don't know how they got it.
There's some fairly good mathematician, and would they need more sophisticated math than this to derive that value?
Or just a really big triangle that they could measure and then do the division.
Maybe they looked
Sorry, what was that?
Maybe they just looked the answer up in the back of the book and just copied it down.
Look on the back of the papyrus, right? That's where all the answers are.
Exactly.
Eat it off the guy next to him, you know.
Yeah.
All right. So let me
Only
ask
the
one more
odd
time.
answers, though.
What's that?
Exactly. Only the odd answers. Can everybody put your SCA name in the chat again? I've only got like 16 of the 20 people who've come in and out. Please.
I wonder if anyone's done a kind of a examination scientifically of how big would they have to make the structure to measure to that precision, or do they really have to have some mathematical tools to derive these things, both they and the Egyptians, that they didn't record?
All you would really need is a good working system of fractions.
Would it also,
Oh, go ahead.
would it also matter what materials you're using? Because obviously, if you're stacking up stones to build a building, you don't have to worry about the metallurgy you would need for, say, a skyscraper, to be exact in your tolerances.
This is true. There's a lot we don't know about ancient mathematics, which is one of the reasons I hadn't taught a class on it before, is because there's just so many unknowns. Like we found all these tablets, and we can kind of like see what's on them. We can see the patterns of what's on them, but like we don't really know how they used them because we don't have a lot of like documentation of people using them. We don't have, there's a lot of context missing from these. It'd be kind of like if you were in 5,000 years in the future and you encountered a calculus textbook and you were like, well, are people actually learning how to do this calculus? Is this their textbook, or are they memorizing this? Like we would have all the same questions about that. But if we didn't have anything like, a scope and sequence from a calculus class, or any recordings of engineers talking about how they used things, you know what I mean? Like inventories of things that were found in archaeological excavations of engineering offices. And then of course there's the whole issue with, the Victorians want to interpret everything as, some kind of blood sacrifice from savages thing. So yeah. We have a long way to go with the scholarship here, and there's just a lot of holes that we're not going to be able to patch.
But one thing I think may be true, if you just wanted to get those numbers from making a really big triangle, if you made something, say, the length of a football field, that's like 3,600 inches.
Yeah.
You could get some pretty good estimates on those numbers, a fair number of decimal places, if you had a triangle that big.
Yeah, that's what I'm thinking that they did.
That's why I'm just curious if anyone's calculated that. Would it need to be, size of a building, size of a football field, size of a town?
I'm not sure. I'd have to do a little back of the envelope stuff to figure that out.
Because even size of a football field, they might have done it mathematically first, and we just don't see how.
Yeah, we just don't know.
That sounds like an ANS project waiting to happen, right?
Yes, but not for me. I'm here to inspire you. I shall be your inspiration.
And to be credited appropriately for that inspiration.
Yes. For more information, here is a really good book, The Universal History of Numbers by Georges Ifra. This is a good book there for people who want to get into it. I know it's kind of a large book, but it's got a lot of packed information. It's very, very dense. If you're more into the Egyptian side, this one, Count Like an Egyptian. This is a nice one. Count Like an Egyptian by David Reimer. And then this is another source that I've drawn on for this is the Historical Roots of Elementary Mathematics by Bunt, Jones, and Bedient. So this is another good one. And the cat is making his appearance. Hello.
Would it be possible to get the ISBN numbers of those books?
Yes.
It just makes it easier to get into library loan.
Let's see. The Historical Roots of Elementary Mathematics is 0-486-25563-8. Count Like an Egyptian. Where's that ISBN? Gotta be here. Here we go. 978-0-691-16012-2.
Can you repeat that?
Yeah. 978-0-691-16012-2. And then the Universal History of Numbers, 0-965-045501. I know some of those are older ISBNs because these are older books. I've had them for quite some time.
I think I copied them all into the link into the chat as you were saying them. So if
All
someone
right.
needs them, hopefully they're there.
All right.
Thank you very much.
How can we contact you and maybe get a copy of your slides?
So there is a folder. Give me a second to pull up the folder that has all of the handouts and the slides in it, and it will also have the recordings when we're done. And I am putting that in the chat right now. That's the folder that currently has the slides and the recordings, or sorry, not the recording, the slides and the handouts, and it will have the recordings. Thank you, everybody. I appreciate your attendance.
Cool. Is there a way we can contact you, or is that listed somewhere in
for
your
me,
docs?
yes. You can email me at sarah.brilliant. Yes, that's my real maiden name. .thomas@gmail.com. And just FYI, it's going to be in about half an hour. The other class, the part 2 class, is at a different link. It's at, hang on. Do we have the link, James?
I don't have it.
Okay, I'm
Well,
getting
I have
it.
it in the email that it was sent to me, but let me see if I can pull that up. I am the Luddite.
Here we
in the
go.
room.
I've got it. Oh, let me check. Oh, no, that's not right.
If it pastes, woohoo!
Did it paste? Yay!
Yep. Take
All right.
off the login info part, and that should be it.
All right. Thank you, everyone. We'll see some of you in about half an hour.
Oh, does